at this bird flying. Can you think of some functions related to its motion? We saw two such functions earlier. The distance traveled as a function of time and its speed too as a function of time. But we also know that as the altitude rises, the atmospheric pressure decreases. So, the atmospheric pressure felt by the bird is the function of its height above the ground. We previously saw that when we have two quantities, x and y, such that for each value of x, there is one value of y, then we say that y is a function of x. So here x could be time and y could be the distance. X can be the altitude and y the atmospheric pressure. X could be time and y the speed. Can you think of other functions like these? Let me give you one example. What do you think the position of a book in a library is dependent on? Each book in a library is labeled using letters and numbers like these. And these letters and numbers could be based on the subject or the genre or edition maybe. So the position of the book is dependent on some letters and numbers. Any more examples that you can think of? Share your thoughts in the comment section below. But just knowing that two things depend on each other isn't very useful to us. We need to know how they are related to each other. Previously, we saw that this relationship can be given by equations like these. This equation says that the value of the dependent variable is the square of the value of independent variable. But can a function like the position of a book in a library be represented like this? No, we cannot do that, right? We cannot represent this function by an equation like this. In calculus, we only deal with functions between two things that can be quantified. Such quantifiable functions can also be represented visually. Do you remember the question we asked in the previous video? We asked what's common between this equation and a flashlight or a dish satellite. Did you find anything? The mirror in this flashlight and this dish are similar curved surfaces called parabolic surfaces. The special thing about such surfaces is that in the case of a satellite, all the electric signals falling on the dish get reflected to this point called the focus. And in the case of flashlight, it's the opposite. The bulb inside is located at the focus point. When we turn it on, all the light rays, instead of spreading in all directions, get reflected in the forward direction. Now look at the cross-section of the curved surface. Notice that the whole surface is made up of curves which look like this. We've seen earlier that this type of a curve is called a parabola. And here's the connection. This curve is the geometrical representation of this equation. Or we can say that this equation is the algebraic representation of this curve. Now let's say we draw x and y axes like this. The values of independent variable x are represented by the points on the x-axis. And the values of the dependent variable y are represented by the points on the y-axis. Here, the x and the y coordinates of the points on this curve are related based on this relation. If we take different values of the constant k here, we will get different functions. And for each function, we can draw a curve corresponding to it. Just by looking at them, we can figure out how the two functions behave relatively. As the value of the variable x increases, the value of the variable y increases relatively faster in this case. Visualizing a function gives us an intuition about how it works. Now let me ask you a question. In our previous video, we found out the rate of change in the dependent variable with respect to the independent variable for this function. We get this new function for the rate. So here, can you tell me what this rate means geometrically? Think about it and share your thoughts in the comment section below. So in this lesson, we saw that a function can be represented by its equation and its graph. Now look at this curve. Can you tell me whether this curve represents a function or not? We will continue this in the next part. This curve does not represent a function. Let's understand why. For now, let's first assume that this curve represents a function. We usually denote a function in this way. It's read as f of x. This notation is made up of three things. First, x here represents the independent variable. Second, f represents the function itself. Third, f of x together represents the dependent variable, which we earlier denoted by y. Another way to write it is y equal to f of x. So this tells us that the variable y is some function of the variable x. And that function is denoted by the letter f. Such type of notations also help us when we want to talk about two different functions between the same variables. We can denote them using different letters like this. Now let's come back to our question. Look at this point on the x-axis. We denote it by x1. Now we see that related to x1, there are two values of the variable y. And that's why this curve does not represent a function. We have seen that a function is a relation between two variables such that for each value of the independent variable, there is only one value of the dependent variable. But if we draw a line parallel to the y-axis here, we see that for one value of x, there are two values of y. So this is not a function. Drawing a vertical line like this helps us. For example, look at this curve. If we traverse this curve through a vertical line, we see that at some points, the line intersects the curve at more than one point. So this curve cannot represent a function. Checking whether a curve represents a function in this way is called the vertical line test. Now let's get back to this function and its geometrical representation we saw earlier. Notice that in this equation, for any value of the variable x, we get one value of variable y. This can be easily seen from its geometrical representation. But now look at this function. What will be the value of the y variable for x equal to 1? For x equal to 1 here, we get 1 divided by 0. Anything divided by 0 is undefined. Now, if we draw its graph, it will look like this. So we see that this function is not defined for x equal to 1. But for all other values of x, we will get one value of y. So except for x equal to 1, the function is defined for all the other values of x. Therefore, we always have to mention the collection of all the acceptable values of x. It's called the domain of the function. And the collection of all the values of y related to the values of x in the domain is called the range of the function. Now we have an idea about the concept of functions. Now let's say we have sets x and y, both of numbers, and we're given this relation between the two sets. We can see that related to each number in the x set, there is only one number in the y set. So this relation is a function. It can be written like this. The domain of the function is the numbers in the set x, and the range of the function is the numbers in the set y. But look at this relation between two sets of numbers. Is this a function? If it is, then what's its domain and range? Yes, it's a function. Related to each number in set A, there's only one number in set B. It doesn't matter if there are more numbers in set A that are related to a number in set B. So what about the domain and the range? Here, the domain is this set of numbers. But now notice that this number in set B is not related to any number in set A. so it's not in the range of the function. The range will be the set of these two numbers. So we can now talk about functions in a general sense. Let's move on to a new page. Here is a set of things, and related to each of its elements, there's only one element in some other set. This relationship is called a function. And how they are related is usually given by an equation or shown pictorially with the graph of the function. Now let me ask you a question. Why exactly are we looking at the concept of functions in calculus? As we move along, we will realize that all the problems we discussed about in our previous videos can be framed in terms of functions between two variables. Let's say we are given this graph of a function. Then finding the solutions of the problems we discussed earlier boils down to two things. First, to find out the steepness of a tangent line at a point on the curve. Differentiation is the process that's used here. Now the second thing is to find the area of the particular region like this under the curve. Integration is the process used here. In the upcoming lessons, we will see how exactly this is done. To stay updated, subscribe to our channel by clicking here. Happy learning!